Good morning, class. We are looking at Calculus 1, Chapter 2 review, limits and derivatives. Exam 1 will cover sections 2.1 to 2.8. And here's the first part. 2.1, the tangent and velocity problems. 2.2, the limit of a function. 2.3, calculating limits using limit laws. Calculating limits using the limit laws. So we are going to cover in this chapter the tangent and velocity problem, the limit of a function, calculating limits using the limit laws, the precise definition, continuity, limit at infinity, horizontal asymptotes, derivatives, and rates of change, the derivatives as a function. All right, so let's get started with the concept of a limit. As far as limits are concerned, we can find limits by numerical and graphical method, also analytic or algebraic method. The definition, how do we read this? We read the limit of f of x as x approaches a equals a. So the limit of f of x as x approaches a equals l, which means we don't care what happens at x equals a, but rather when we get closer and closer to that. For example, if you look at all of these graphs, and we are interested in this limit as x approaches a, if we approach a from the left or right, from the left, we are in this portion. From the right, we are in this portion of the graph. From the left, it's taking us towards the y-coordinate L. From the right, moving towards the same point. Meaning, in all three cases, we are getting closer and closer to A. We are getting closer and closer to this point on the curve y equals f of x. We are getting closer and closer to this y coordinate. Therefore, the limit of f of x as x approaches a in all three cases is the same, namely L. However, there are some differences. F of a is precisely equal to L in the first case, part A, which means it's continuous at x equals a. F of a is not equal to L because there is a hole here, there is a discontinuity. So what is f of a equal to? Something else, B. In this case, what is f of a? There is a hole here. It's not even given to us. We don't know it. It's undefined. Therefore, we say part A f of a equals L, part B f of a equals B, which is not equal to L, and in part C f of a is not defined. But in each case, regardless of what happens at A, the limit of f of x as x approaches a equals a. So the limit has got to do with getting closer and closer to the value of interest, but we never get there. Horizontal asymptote. It has a specific definition in calculus. If the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity is N, then we say HA, short for horizontal asymptote of the function y equals f of x, as the equation y equals L. That's the definition. Here's the definition of a VA, short for vertical asymptote. If the limit of f of x as x approaches a, or this is called a from the left, this is called a from the right, it's either negative or positive infinity, then x equals a is a vertical line that represents the vertical asymptote of the function. This is known as one-sided limits. A function has a limit at a if one-sided limits are identical, meaning the limit of f of x as x approaches a from the left equals L, and the limit of f of x as x approaches a from the right is L. Therefore, the limit of f of x as x approaches a equals n. So one-sided limits must be identical for this to work. Okay, one-sided limits must be identical for this to work. And that gives rise to what is coming up later on, definition of a continuity where limit of f of x as x approaches a is equal to f of a, meaning if the limit and the functional value are the same, the function is considered to be continuous at that point. All right, let's look at this example. Finding limits by numerical and graphical method. We have the function x minus 1 over x squared minus 1. It says guess this value, limit of x minus 1 over x squared minus 1 as x approaches 1. And let's see how we approach that. Notice if we call this f of x, this expression x minus 1 over x squared minus 1, f of x is x minus 1 over x squared minus 1, is not defined when x equals 1 because it makes the denominator 0. Does it matter? And the answer is no, because we are not saying x equals 1. We are saying x is approaching 1. So numerical method says, okay, let's make up a table. Okay, the tables below give values of f of x correct to so many decimals, in this case 6 decimal places, for values of x that happen that approach 1 but are not equal to 1. So first of all, this piece, we're going to call it f of x equals x minus 1 over x squared minus 1. And since x is approaching 1, we're going to look at both sides of 1. From the left side, x less than 1, please understand 0.5, 0.6, 7, 8, 9, those are way off. So we get closer like 0.99, 0.999, and so on. And when we do that, it gives rise to these answers. From the right side, when x is larger than 1, for example, 1.5, 1.4, 1.3, 1.3, 1.2, 1.1, we are getting closer and closer to 1, 1.01, so on and so forth. And as we get closer, we get to those values. So please understand, from the left, so far, what we have, this is the closest number. From the right, this is the closest number to 1. And if we look at this last one, these two values suggest from the table, this limit must be equal to 0.5. Okay, so that should be the suggestion. So that's numerical approach. Numerical approach gives us 0.5. If we were to graph this, you can, for the sake of argument, you can even use a graphing calculator. There's a hole here, and the reason there's a hole here, when you graph any rational function, first and foremost, you put it in lowest term, and you exclude what makes the denominator 0. So you can't say x squared minus 1 equal to 0, and that gives you two vertical asymptotes. That's not the case. First, you have to get rid of the common factor, and that gives rise to a location of a hole. So from the graph, as we approach 1 from the left and right, meaning here and here, it gives us getting closer and closer to 0.5. And so the graphical approach gives us the same answer. But more importantly, the analytic or algebraic approach is important. This is x squared minus 1. It's in the form of a squared minus b squared, which is a minus b times a plus b. By the way, 1 can be 1 squared or 1 cubed, makes no difference. The common factor of x minus 1 is dropped. And if we plug in we get 1/2 or 0.5. This is the best approach, algebraic or analytical approach. So in all cases, numerical method, graphical method, algebraic or analytical method, we ended up with the same answer, everybody. All right, let's move on to limit laws. Let f of x and g of x be defined for all x not equal a over some open interval containing a. Assume that L and M are real numbers such that the limit of f of x as x approaches a is given as L, and the limit of g of x as x approaches a equals M. Remember, when we are discussing limits at x equals a, what happens is not of interest to us. In fact, the function may or may not even be defined. That's why it says it may not even be defined at x equals a. So the limit of f of x as x approaches a is given as L. The limit of g of x as x approaches a is equal to M. And let c be some number, some constant. Let c be a constant. Then each of the following statements holds. This is the sum law. The limit of f of x plus g of x as x approaches a is the limit of f of x as x approaches a plus the limit of g of x as x approaches a, L plus M. Meaning, the limit of the sum is the sum of the limits. Difference law. The limit of the difference is the difference of the limits, L minus M. Constant multiple law. The limit of c times f of x as x approaches a, you can c is a number, is a constant, is a multiplier, is a coefficient, you can take it out. So it becomes c times L. Product law. The limit of the product is the product of the limits, L times M. Quotient law or rule. The limit of the quotient is the quotient of the limits, L over M. Needless to say, as always, the denominator cannot be 0. If it is, then the limit doesn't exist. If the denominator is 0, the limit does not exist. The power rule, the power law says the limit of the power, okay, if we raise it to the power, is to find the limit first and then raise it to the power, L to the power of N. So the limit of the power is the power of the limit. And the same thing, if you want to take a root, so the limit of the nth root of f of x as x approaches n is the nth root of the limit of f of x as x approaches a, therefore it's the nth root of L. Of course, for all n, if n is odd, remember if it's even, the radicand must be positive because otherwise it's an imaginary answer. So for n being odd, there is no restriction. For n being even, this must be positive. We also have direct substitution property. A continuous function at a has the following limit value. The limit of f of x as x approaches a equals f of a. So simply put, just plug in. That's the idea, everybody. Just plug in. Functions with the direct substitution property are called continuous at a, are called continuous at a. And we're going to discuss the squeeze theorem with more details when we come across it, but in short, if the g function is between f and h, so f of x is less than or equal to g of x, less than or equal to h of x. So g is some function that is between the two when x is near a, except possibly at a. It doesn't matter what happens at a, okay? We are interested near a. So the limit of f of x, the left side, as x approaches a, is the limit of h of x, the right side as x approaches a. Therefore, the limit of the function in between, the limit of g of x, as x approaches a, must be the same, namely L. Okay, that's important to understand it. Let's look at this graph. Again, the graph is given to you. If you try to graph it, you may miss something. So just pay attention to what is given. So for this function, we want the limit of f of x as x approaches 2. That's why we want to look at limit of f of x as x approaches 2 from the left, from the right, and then x approaching 2. So let's quickly go over that. I want to make sure we understand what's going on. So if we look at number 2 along the x-axis, on the left side, we are moving this way. That means we are moving this way, this portion of the graph. And we are moving towards this point, which has a y coordinate, which is 3. So one more time. Here's number 2. The left side of 2 puts us in this portion of the branch. We are moving towards this hole, and this has y coordinate 3. But from the right side, of number 2, we are moving this way. So from the right side of 2 puts us in this branch of the function. We are moving towards this hole. Remember, we never get there, so it's not important it's a hole or not. The fact of the matter is we're talking about the limit. So at this point, as a y coordinate 1. Are these two identical? No. This limit, D and E, does not exist. Does not exist. Because one-sided limits are not identical. Now let's look at f of 2, the limit of f of x as x approaches 4, and f of 4. So it is important to distinguish between the concept of a limit and a functional value. So let's look at f of 2. Can anybody tell us what is f of 2? When we are asked to find f of 2, that means precisely at x equals 2, what's the y coordinate? Precisely at 2, look for a solid point. This point is solid and has the y coordinate 3. So f of 2 equals 3. What is limit of f of x as x approaches 4? Here's number 4. From the left side of number 4, we are moving this way. From the right side of number 4, we are moving this way. And whether we approach it this way or that way makes no difference. In both cases, we are moving towards this hole, which has a y coordinate 4. Therefore, the limit of f of x as x approaches 4 does exist, and it's equal to 4. But what is f of 4? Well, at 4, look for a solid point. I don't find any. What is f of 4? I have no idea. It's not given to us. We say it's undefined. Does the limit exist? Yes, because we never get to 4. We get closer and closer to 4. By the way, we will discuss this later on, these two are the same, which means the function is continuous at x equals 2 from the left. That is something we discuss later on, but for now, we wanted to discuss the limits. Here's the function, the limit of r of x as x approaches 2, 5, negative 3 from the left, negative 3 from the right. So we're going to start with number 2. So number 2 coming from the left and right, of number 2 makes no difference. It's taking us down, way down to negative infinity. Number 5, when we approach 5 from the left or from the right, makes no difference. It takes us to infinity. Now, negative 3 from the left means going this way. So negative 3 from the left goes towards negative infinity. From the right, positive infinity. I'm reminding you of this definition. We said if the limit of f of x as x approaches either a or a from the left or a from the right is negative or positive infinity, makes no difference. X equals a represents the equation of a vertical line, vertical asymptote. So the question is, what are vertical asymptotes? Well, this one suggests x equals 2 because it's approaching negative infinity. This one suggests x equals 5 because it's approaching infinity. Both of these, negative 3 from the left and negative 3 from the right, one of them goes to negative, one of them goes to positive infinity. Both of them suggest x equals minus 3 is another vertical asymptote. X equals negative 3, x equals 2, x equals 5. Those are vertical asymptotes. Remember, vertical asymptotes are not part of the graphs. They help us graph the function. That's why they are dashed lines. They are not solid. To find the limit, just plug in and observe. So what happens when we do that? If it gives you a number, any number, you're done. If it gives you 0 over some number other than 0, 0 over any number other than 0, that is also 0. And you're done. 0 over 5, 0 over 2, 0 over negative 10, who cares? 0 over infinity, 0. What if it gives you some number over 0? Remember, when we have a number over 0, it blows up either to infinity or negative infinity. Which one? You have to figure out, but it's one of the two, and I'll show you how easily you can find which one is the answer later on. However, in calculus, most of the time we end up with a form known as indeterminate forms, such as 0 over 0, infinity over infinity, infinity minus infinity. 0 over 0 or infinity over infinity doesn't mean it's equal to 1. Infinity minus infinity doesn't mean it's equal to 0. Could be any number. That's the meaning of indeterminate. And for me, when I get to indeterminate, I'm going to call it, to me, indeterminate means more work. What do we mean by more work? Well, I mean, we have to use our algebraic techniques. To figure out the answer. Algebraic techniques. Here's an example. If you plug in 0, this becomes square root of 4, which is 2. 2 minus 2 is 0. This is 0, so we get 0 over 0. So plugging in, we get 0 over 0. And so we have to use some sort of a technique to fix the problem. Whenever you have a square root, the technique is the conjugate. The conjugate for a plus b is a minus b, and the result is a squared minus b squared. Because this is 0 over 0, so this is 0 over 0, and because this is square root, we are going to use the conjugate. The conjugate for a minus b is a plus b, and their product is a squared minus b squared. So what do we do here? We are going to multiply and divide this fraction by the conjugate of the numerator, which means we keep this and we change this to a plus sign. And the reason we multiply and divide, because this expression equals 1. Otherwise, we can't do that. So what happens in the numerator, and that's extremely important, nothing. You keep the numerator as a product. And now you multiply the denominator, you keep him as a product. The numerator, you're going to multiply him using the fact that it's a conjugate, okay? And so when you multiply the top, square root of x plus 4 gets squared up and comes out minus 2 squared, and we get this one. One of the things that sometimes students make a mistake, I want to remind you, is that 2 squared is 4, minus 2 quantity squared is 4, but minus 2 squared is negative 4. So it's a matter of order of operations. 4 and negative 4 cancel each other. X and x cancel each other. If you plug in 0, square root becomes 2. 2 and 2 is 4. The final answer is 1 over 4. So algebraic techniques, when we get to 0 over 0, which is one form of an indeterminate form, we use our algebraic technique. So we're going to continue on that thoughts. Okay, and so let me just erase everything so we can use that. Whether we approach -3 from the right or left, ultimately the two of them become -1 over 0. Okay, now it's extremely important to know, if you have any number, let's say 5, you approach it from the left or right, makes no difference. It's positive. Are you with me? 10, 20, 30, both sides are positive. If you have -5, both sides are negative. However, 0 is the only number. The right side is positive, the left side is negative. That's why you need to know what happens to 0. As far as the numerator is concerned, -3 from the right, okay, makes it -1 or -1.00001 or -0.999. It's almost -1. It is the 0 in the denominator that makes a difference. So how do we figure this out? If you plug this in by picking up an example of a -3 from the right, means something like, let's say, negative 2.9. If I add it to 3, what do I get? I get positive 0.1, so it's 0 from the right. However, if you look at this one, negative 3 from the left, example, negative 3.1. Please understand this is negative 3 class. From the right side, like negative 2, right? Negative 2.9. From the left, like negative 4 or negative 3.1. If we add it to 3, we get negative 0.1, so 0 from the left. So what does it mean? When you have a number divided by 0, it blows up to infinity. But is it positive or negative infinity? Negative over positive is negative infinity. Negative over negative is positive infinity. The reason I want to find whether it's 0 from the left or right, because I want to figure out the answer is positive or negative infinity. And you have to do that if you want to get to the answer easily. Okay? You want to find the following limit. If you plug in, and I leave it for you to check it, you get 0 over 0. And that is an indeterminate form. The technique is factoring. Now, the numerator is very easy, x times x minus 4. But in general, to give you an idea how you want to factor, of course, you want two numbers. The product is negative 4, the sum is negative 3. But one of the things that can help you figure out what's going on, if you take a look at this one, when x approaches 4, and you're getting 0 over 0 because the denominator must have a factor of x minus 4. So if x is approaching 4, we must have a factor of x minus 4. If x is approaching 7, we must have a factor of x minus 7 most of the time. But if it's approaching, let's say, minus 5, then we should have a factor of x plus 5. So as you can see here, we do have a factor of x minus 4. And therefore, that will help us with the factoring also. And now if I plug in 4, plug in and you get 4 over 5, and we are done. So the technique in this example is factoring. What about this one? Plug in first. And if you plug in, you get 0 over 0. Because the numerator involves square root, the technique is the conjugate of the numerator, which means you change this to a plus 1, you multiply and divide by it. Again, the reason you do that because this is equal to 1 and it's acceptable operation. You're multiplying by 1 in essence. So what happens to the denominator? Absolutely nothing. You keep it as a product. Why is that? Because h is approaching 0. This is the problem. We are hoping to get rid of it. When we multiply these two, we get the square root of 1 plus h, quantity squared, minus 1 squared in the numerator. 1 plus h, square root of 1 plus h, quantity squared, comes out as 1 plus h. 1 and minus 1 cancel each other. H and h cancel each other. The numerator ends up being 1. If you plug in 0, square root of 1 becomes 1. 1 and 1 is 2. The result is 1/2. So 0 over 0, the technique is factoring. 0 over 0, in this case, the technique is conjugate because the numerator involves the square root. But remember, first you plug in and you observe. We are going to plug in first. It's important not to assume, okay, I'm going to multiply by the conjugate. Plug in and observe. If I plug in, this goes to 0, so I have 3 up here. Over here, I have 6 squared, which is 36, minus 7 times 6, which is minus 42. So the numerator is 3. But what about here? Negative 6 and positive 12 gives us 6. 3 over 6 is 1/2. I'm done. It just works out. All right. The limit of 1/3 minus 1 over x minus 3 as x approaches 3. If I plug in 3, I get 0 over 0. And what's the technique? This is called a complex fraction. The technique is to multiply and divide by LCD. Notice we have 1 and 2 fractions in the numerator, nothing in the denominator. Even if you have more in the denominator, all of those fractions, you find the LCD, which happen to be 3x. You multiply everything by it. That means the numerator as well as the denominator. This is the fastest process to change a complex fraction to a simple fraction. Again, what happens to the denominator? Nothing. You keep it as a product because x approaching 3 makes this 0 and you're hoping to get rid of it. Nothing. If you apply the 3x to 1/3, you get x, and to this one, you get 3. So x minus 3. You simplify by getting rid of x minus 3. You plug in number 3, and the final answer is 1 over 9. 1 over 9. We are going to move on. Evaluate the following limits if they exist. We are interested in the limit of f of x plus 5 g of x as x approaches -2, where f of x is this red function and g of x is this blue function. We are going to use the limit laws and separate them as the limit of f of x as x approaches -2 plus 5 times the limit of g of x as x approaches -2. We are using the limit laws. And now all we have to do, find this piece, the limit of f of x as x approaches -2, and then this piece, the limit of g of x as x approaches -2. So let's find out. What is the limit of f of x as x approaches -2? Well, this is number -2. Here's the left side, and here's the right side. Here's the left side, and here's the right side. Meaning, whether I approach -2 from the left or right, -2 from the left in this branch of the graph takes me there. From the right takes me to the same spot, which has a y coordinate equals 1. So the limit of f of x as x approaches -2 equals 1. For the g function, the blue function, from the left, from the right, both of them are moving towards this point, and this point has a y coordinate -1. Therefore, this is 1 plus 5 times -1, which makes it negative. So it's pretty straightforward. What about x approaching 1? The limit of f of x times g of x as x approaches 1. And to do so, we're going to separate this into limit of f of x as x approaches 1 times the limit of g of x as x approaches 1. And we're going to figure each one, starting with the first one. So what is the limit of f of x as x approaches 1? And here's number 1, by the way. So let's do that again. Number 1, the left side, the right side, and the limit from the left, the limit from the right, both of them are moving us towards this point, and this point has a y coordinate equal to 2. So the limit exists for this function. Both sides have the same answer, namely 2. But what about this guy? G of x as x approaches 1 does not exist. DNE y is that. We want to explore that. We're going to look at 1, the limit of g of x as x approaches 1 from the left and then from the right. So let's see what happens from the left. From the left of 1 here, from the left of 1, we are in this part. We are moving towards this point, which has a y coordinate -2. So the limit of g of x as x approaches 1 from the left is -2. But from the right side of 1, we are moving here. From the right side, we are moving towards this hole. And this hole has a different y coordinate, namely -1. Because the one-sided limits are not equal, this limit doesn't exist. Because this limit doesn't exist, this product doesn't have a limit either. So this limit does not exist either. I'm going to quickly show you a different method, okay, just to see how it works. You can start from here and say, you know what, I'm going to find the limit as x approaches 1 from the left and as x approaches 1 from the right, because both of them exist, but they don't give us the same answer. So let's look at this one from the left. So when you want to look at this one from the left, that means look at this one from the left, right? So both sides for this guy doesn't, from the left and right doesn't change, it remains as 2. But from the left, this is -2. So the product of these two numbers, 2 times -2 is -4. Now, the same thing from the right. See, from the right is also 2 here, but from the right is different. 2 times -1 minus 2. As you can see, 1 becomes -4, 1 becomes -2 because they are not identical. Then the limits from the left and right are not the same, and therefore this limit does not exist, everybody. So again, I believe it's pretty straightforward. I hope it is. So one-sided limits are different. So we looked at them 2 different ways. However, to make sure we understand the concept, with more details, let me clean up the mess. I want to explain the idea of f of -2 as well. If you look at -2, we said this number, say this is -1, this is -2. When we want -2, that means go look at a solid point for the f function. This solid point has a y coordinate 2, so the answer is 2. which makes this function discontinuous. Okay, the function obviously has the limit at this number -2, but has a different functional value. Makes it discontinuous at x equals -2. Of course, g at -2 is -1, and so that has no problem. As far as g of 1, if you look at number 1, again, f has no problem, everything is fine. But if you look at this one, the limit doesn't exist, the blue one, but you look at a solid point, this solid point has a y coordinate -2. Again, I want to make sure we distinguish between the concept of a the functional value, the exact value of the function, versus its limit. Those are two different things, everybody, and we really don't want to mix them up. What about this one? The limit of f of x over g of x as x approaches 2. Well, when x approaches 2, let's pick up this color. So this is number 2. We are going this way. We are going this way. And I hope you see that f of x is going this way, and it's probably, I don't know, 1.5 or something. So it has some number. Let's say 1.5. But what about the g? It's equal to 0. Since the denominator is 0, this doesn't exist either. So the denominator approaches 0, meaning the limit of g of x as x approaches 2, right? So the limit for each case exists. But the problem is we are dividing by 0. The denominator approaches 0, while the numerator approaches a non-zero number, and this was about 1.5 roughly. And that's why it doesn't exist. All right, we are interested in finding the following. If g of x is between 2x and x to the power of 4 minus x squared plus 2 for all x, evaluate the limit of g of x as x approaches 1. And we're going to use what is known as the squeeze theorem. If you recall, the squeeze theorem basically says if a function is between two other functions, when x is near a, for example, x possibly at a, and the limit of each one, this one, f of x as x approaches a, and this one, the limit of h of x as x approaches a is the same thing, doesn't matter what l, then the one in the middle, the limit of g of x as x approaches a must be the same, namely L. So that's what we are going to look at. In this case, let's look at the limit of 2x as x approaches 1, and simply put plug in. That gives you 2. Let's look at this case. Let's take a limit of the right side as x approaches 1, the right side of the inequality. And if we plug in, we get 1 to the power of 4 minus 1 squared plus 2, which is also 2. So therefore, the limit of g of x as x approaches 1 must be the same by the squeeze theorem. It is important to mention why. The y is by the squeeze theorem. So if you just wrote that one without writing by the squeeze theorem, it's wrong. So what do we use the squeeze theorem for? There are cases that are pretty difficult to prove. For example, if you want to prove the limit of square root of x times the brackets 1 plus sine squared 2 pi over x close brackets equal to 0 when x approaches 0 from the right, that's pretty difficult. We use the squeeze theorem. And the methodology is this. You start from a known theorem or fact, and then expand it to make it look like this. So one of the facts we know is that sine is between -1 and 1 regardless. So we're going to call it sine of alpha, gamma, beta, or Sine of 2 pi over x makes no difference. Must be between -1 and 1. Sine is between -1 and 1. If I square this, all sides, this becomes 1, this becomes sine squared. It's important to know you don't change it to 1, you change it to 0. Here's the reason. When sine is between -1 and 1, if you square it, the part that is between 0 and 1 keeps it between 0 and 1. So -1 in essence has no bearing, because between -1 and 0 goes to 0 to 1. Between 0 and 1 goes to 0 to 1. So it's important to pay attention to what happened here. Okay, everybody? All right. So we got this part, everybody. We want to make it look like this. So what is missing? 1. So what do? Let's add 1 to all sides. Add 1. This becomes 1. This is plus 1. This becomes 2. So we just added 1 to all sides. That's simple. All right. What is the next step? So far, if you compare this to the brackets, we are in good shape. The brackets and this one are identical. So what is missing? Square root of x. Let's multiply both sides by square root of x. Remember, when you multiply an inequality by a number, it flips over if the sign is negative. However, x is approaching 0 from the right, so square root of x is positive, so nothing changes. If I multiply everything by square root of x, this becomes square root of x, this becomes 2 square root of x, and this one I just put the square root of x in front of it, brackets. Now, this looks exactly like this. In other words, this one is identical to this one. Now I'm going to use the squeeze theorem. I'm going to look at this piece. I'm going to look at this piece, and I take a limit. As you can see, if you take a limit of this piece as x approaches 0 from the right, and this piece as x approaches 0 from the right, both of them result in 0, correct? Therefore, according to the squeeze theorem, the one in between must also have a limit of 0. So we prove the limit of square root of x times 1 plus sine square 2 power x as x approaches 0 from the right is also 0 by what? By the squeeze theorem. You always have to mention that, by the squeeze theorem, everybody. All right, given 2x plus 12 over the absolute value of x plus 6, we want to find the limit of 2x plus 12 over the absolute value of x plus 6 as x approaches -6. So we are looking at one-sided limit. So we're going to look at one-sided limits. In order to look at the one-sided limit, we're going to look at the limit as x approaches -6 from the left and -6 from the right. And to do so, I'm going to remind you that absolute value of x equals x if x is greater than 0. Absolute value of x is minus x if x is less than 0. I hope everybody remembers that. Therefore, absolute value of x plus 6, you can drop the absolute value if x is larger than or equal to -6. And it's the opposite of that expression. if x is less than -6.
Excuse
Now,
me, Professor.
yes, Brian.
What slides are these? Or what section are we?
Uh, I'll go over that afterwards. Let's finish this.
Okay.
So the limit of 2x plus 12 over the absolute value of x plus 6 as x approaches -6 from the left. Because it's less than -6, we are here. And that means the bottom changes to this expression. And the numerator, we can factor the 2 out. We get the limit of -2, which is a constant and becomes -2. On the other hand, if we have this as x approaches -6 from the right, because it's larger than -6, puts us here, and we simply can drop the absolute value sign, and of course the numerator we factor out the 2. And this is the limit of 2 as x approaches -6 from the right, making it 2. Therefore, one-sided limits are different. Because they are different, this limit fails to exist. Therefore, the limit of 2x plus 12 over the absolute value of x plus 6 as x approaches -6 does not exist. Why is that? One-sided limits are different. Here's another approach. If you simplify the expression without the limit, this one becomes 2, this one becomes -2, and it shows the limits are different. One-sided limits are different, therefore the limit does not exist.